digester needs heat. And then one of the big things that people are doing with methane gas now are doing cleaning that gas and doing direct pipeline injection. So taking that methane gas and basically firing up your home stove with it and injecting it into the gas line. So obviously, when we think about renewable resources, anaerobic digestion always comes to kind of mind when we think about that. We don't want to go into everything on anaerobic digestion, but again, it's going over a lot of the same things that Paul went over on BNR and heterotrophs, nitrifiers. All bacteria are very similar to humans. I mean, when we think about what we need for anaerobic digestion, we need to think about our food. We need to think about the bacteria. Who are the players in the game? We need to mix it. What does that configuration have to look like? What about heat? A lot of times in our liquid stream, we don't get to control the heat. In a digester, we're controlling the heat. And then how long do we need to keep it in there? Our SRT. So SRT, all these terms are very familiar with everything that you went over in the liquid stream. We just have, the biggest thing about it is we have new players. They're not aerobic anymore. They're anaerobic players. The general, and we're not going to dive into kind of each one of these today. We're going to go over the general bacteria, the general transformations and what's going on, and then really get into how it links to BNR. And basically a lot of this, there's the spring training that we have now that we do. It's this 2.5 days of liquids training. TRA also does a solids training where it's 2 days of just digester and solids training. And so with that, essentially what TRA kind of has now, and I think who's in the solids process here at Cruise? We got 1, 2, 3, 4, see 4 people. And it's a lot of like cross-linking and start doing some cross-training. So for some of those facilities like Red Oak, Denton Creek, a lot of those don't have necessarily specific solid staff and liquid staff, right? Does any of the regional plants have? Is it all Mountain Creek? Everybody's all the same staff, right? Yeah, all the same staff. Not like solid staff. I think North Texas, some of the plants have specific solids task. So the effort here is to make sure that everybody is understanding what's going on in each other's court, because it does have impacts. You impact each other, especially when we start talking about nutrient removal and hitting low nutrient limits. So the 3 main steps of anaerobic digestion, really from a big picture, we talk about hydrolysis, and we'll go through each one of these. Acetogenesis, and then methanogenesis. And the methanogenesis, really easy to remember, they're the ones creating the methane. And these guys are the ones creating the acid. And this one is really the one first breaking down our particulate material into a soluble material. So the hydrolysis is the first step. And it's really where we're taking our food. And when we look at food, we're looking at like fats, proteins, like amino acids. We're looking at carbohydrates. And just think about the normal things you eat. You're thinking about breaking those down. We're trying to break those down into liquid soluble forms of those. And that's what that first hydrolysis step is really doing. It's taking particulate matter and breaking it down into soluble matter that bacteria can actually cross through their membranes. Right? If we think about a bacteria, we have a membrane, and we've got to have things cross through that membrane so the bacteria can process it inside their membrane. And so when we get them into soluble forms, they're much smaller, and they can transport through membranes. What usually takes the fermentation step, it's what we call fermentative bacteria. And it's really the rate-limiting step in anaerobic digestion, or we're really limited by the kinetics in this breaking down of particulate matter into that liquid matter that we can actually break down with our methanogens and our acetogens. When we talk about fermentative bacteria and fermentation, that should sound pretty familiar to a lot of people. I mean, how many of you think you have fermentation going on in your plant? See hands. See hands for people that don't have digesters. Where is it happening at plants that don't have digesters? Gravity thickeners. If you leave that gravity thickener in the summer and it's underloaded, what's that patch going to smell like when you pick that up? Where you store sludge. Where you store sludge. You have sludge storage tanks, and especially if it's like primary sludge. And that's a lot of times, I think the word that's thrown around a lot, like septic. When something's septic, it's fermented. You're kind of throwing things around, really the same terms. fermented bacteria are kind of like that official term. And really in typical mesophilic anaerobic digestion, these fermented bacteria are the ones that have to do the first step. Nothing else can take place until they get that first step going. And it is what causes us to have larger reactors sometimes. And so this thermal hydrolysis process is what TRA is putting in, and that's that process right here. This is that thermal hydrolysis process. And notice hydrolysis is in the name. And so our first step is really looking at this hydrolysis step. What TRA, instead of relying on fermented bacteria, what TRA is doing at this point is they're using thermal hydrolysis and utilizing pressure and temperature to essentially break down and explode all of the particulate matter into soluble products. And so essentially imagine taking your wastewater solids, putting them in a pressure cooker and cooking it and actually pasteurizing it. That's where you get class A. So you're cooking at a high temperature and pressure for a set amount of time to pasteurize it and basically kill any pathogens and bacteria in it. But it also gives us our products. And these products are food for our acetogens and our methanogens. So this complex stream of pipes and tanks is what a thermal hydrolysis looks like, THP. We don't want to spend a lot of time on this, but essentially what you're doing is you're going in, you're starting to heat up your solids, and you're going in, each one of these are little batch reactors that you fill. One of them might be reacting, one of them might be filling, one of them might be emptying. And they're going to hold in there for like 30 minutes. So it's basically cooking your sludge for 30 minutes. So the cruise solids people, what does cooked sludge look and smell like when it comes out and you take a sample of that? Like coffee. That's actually a compliment to it. I would say the consistency becomes more like in my mind, it's like tar almost the way it flows. So it becomes very interesting, and it doesn't. It's 16. They feed it in at 16% solids, comes out at 12% solids. 12% solids is usually getting close to stackable. This flows like water. The 12% solids that basically flows like water.
It's not like
It's not as bad. The smell isn't as bad as you think it'd be.
4%.
All right. So the drivers for why TRA is installing THP and digesters for that matter are really producing this Class A sludge. It's improving that degradability footprint. So footprint on there. What you're looking at is, does anybody know what you typically feed? And cruise solids guys, you can't answer. What are we typically feeding an anaerobic digester percent solids? I heard 4 to 6, whatever you can get out of your plant. THP digesters, you're going to feed around 10%. So you're feeding double the concentration, and obviously double the concentration, I can halve my volume. But that's really part of it is this footprint side and getting it on the site. So if you were to look out the window over here and see those digesters, you'll see 3 digesters. If they didn't have THP, there'd be 3 more of those digesters out there. So yes, this THP system may look kind of complex, but it comes on a skid and you install it. It's a lot of mechanical equipment, but it does save that digester side. And the biggest benefits of this Class A sludge, the gradability and that sludge viscosity, because the way they were describing it, how it flows at 10% solids, it flows very well. You can actually mix it. The reason we don't feed regular digesters above 5 or 6%, you can't mix it. But this stuff, because it's been basically all the cells have been homogenized, they've been lysed, we've broken apart everything. They're not sticking with each other anymore. Any questions on the THP? We'll get into the biology now, but I wanted to kind of set that first step up.
So you're doing belt press that. So the belt press is running, 2 watts and primary together. But imagine there was 16% production, 16% cage.
Solids, guys, what are you getting on presses with your primary sludge and WAS before digestion?
26. Okay, scenario 8 on a good day.
28. They're getting less now. Probably getting 22% now. Yeah. You're getting your reduction in the digesters. The biggest thing here is anaerobic digestion releases a lot of phosphate, especially since they're bio-P plant, and you're breaking down cells, so there's phosphorus in here. Leon's going to talk tomorrow about phosphorus impacts in terms of not just liquid stream, but also kind of a little bit of fate and transport, how phosphorus comes from the digester back to the plant. But phosphorus, in the form of phosphate, soluble phosphorus, ortho-P, decreases dewatability. And TRA is witnessing that firsthand right now with the amount of polymer. They used to dose, and Daniel or somebody correct me if I'm wrong, maybe 5 pounds per ton of polymer. Lower, 3 tons. What are you at now? 20? Above 15. It's probably going to be, let's do 15 to 20. So it basically took their polymer dose up 4 times. So it's a significant, and it's overcoming that ortho-P side of it. That's the biggest part you're overcoming here, is the ortho-P.
Back then, we needed to run 6 and really 7 belt presses to keep up. We can run 3 belt presses and maintain. Significantly. I mean,
How many trucks per day left cruise? 25 trucks a day. What are you down to now? Wait, I heard how many trucks? 40 trucks a day. How many trucks are you having now?
right now, it's good.
Daniel, Russ, how many trucks a day? 20. So half the trucks per day. Yeah. So
That's all 50.
any other questions on THP side? After THP, basically we're feeding into a typical digester. And in a typical digester, we have 3 primary bacteria that are doing the work for us. We have what we call acetogenic bacteria and acidogenic bacteria. They both suck to say back to back. And then methanogenic bacteria. And really this is kind of like an assembly line. The acetogenic and the acidogenic are really taking this biomass, or basically our products coming in, and they're making acids. They're making acids and hydrogen, essentially is what's going into here. The methanogens need acids and hydrogen to make methane. So it's essentially this assembly line where these guys got to do their work first before these guys can do their final work in the end. And when we start thinking about anaerobic digestion, I think I ate too much at lunch today. When we start thinking about anaerobic digestion, these 2 bacteria here, let's start comparing to maybe like your heterotrophic bacteria in your VNR aeration basins. These guys grow faster. They're easier to maintain. They can actually go gangbusters and create a lot of acid. When you talk about like an upset digester, a sour digester, that's where the pH is tanked. It's because you started up a digester and these guys get going fast. The methanogenic bacteria, I like to compare them to like nitrifiers. These are our sensitive guys. They need to be coddled. They're very sensitive to upsets. And as soon as our acids, they like acid. They need acid to make methane, but they don't like a lot of acid. You got to get the acid just right. And so really, if these guys work too fast to make too much acid, these guys slow down, which makes more acid, which makes these guys slow down, and it becomes a cycle. But essentially, this is kind of that assembly line to DS, destruction, and methane production. And a complicated diagram of that is this basically where we started at hydrolysis. We started those carbohydrates, proteins, and fats. In the middle here, we're breaking down into to acids, and that's where we're getting down to our acetate and our hydrogen to really make that methane at the end. So in terms of what the cruise solids operators were thinking about before, they had to think about what? How do I get primary sludge and WAS, and how do I make cake, and how do I put it on a truck? There was TSS. It was TSS. They were thinking in terms of TSS. Now you're not thinking no longer in terms of TSS. We're starting to think about, well, what is the cell made of? What is our feed characteristics? Is primary sludge, do we think primary sludge is going to digest like WAS? Primary sludge is going to have like fats and oils in it. WAS is going to have these proteins, amino acids, carbohydrates in it. And they're going to digest very differently. And it's the same thing when we talk about, like on our BNR side, you wouldn't want to kind of quickly change from going from a maybe 50-50 ratio to 60-40. That's a big change. You're changing that food dynamic a lot in that digester. And you're going to notice upsets. When they notice upsets, what do you guys see if the dynamics change a little bit? What jumps up on you? The acids jump up. They'll watch their acetate, their BFAs. See this acetate jump up because, again, these guys, the methanogens are sensitive. We've changed the feed. These guys react well to a changing in feed. They just keep plugging out acid. Acetate. And so what they notice, they'll see a buildup of acids. That's one of their indicators, is they're watching that acid number. So, any questions on anaerobic digestion? We're going to get into, that was my high-level review. No more detail, but Dan, go ahead. Natural buffers. So as we, digesters, and I didn't get into it up here. Nope. So what when they're creating all of this, they're creating the acid, like you said. We also have CO2 and ammonium. We're creating CO2 and ammonium, and you imagine this headspace, a bunch of CO2. Eventually, what happens is that CO2 starts to become soluble. CO2 is a gas, but if you have a high enough gas, it's become soluble, just like DO goes into water, oxygen goes into water. That CO starts to go into our digestion solubilized, and it makes alkalinity. So the alkalinity in these digesters is around 7,000 milligrams per liter. The acids in these digesters are around 400 to 500 milligrams per liter. So you're it's basically a self-buffering system. Some plants do have like external alkalinity there. Rare they use it. TRA has no external alkalinity feed facilities. They did use a buffer during startup. They ran into a period during startup where they had some totes on site and adjusted it for a week. About a week.
That was longer.
Yeah. So during startup, it's recommended that you have a buffer to help in case these guys work too fast and buffer it out. Good question though. So yeah, the acids would be a problem if it wasn't for that alkalinity. Okay. So that was the kind of anaerobic digestion overview. We didn't really dive into a lot of the dynamics. This is a BNR course, so we want to keep it as related to BNR as we can. So now we're going to start looking at solids and liquids interactions, and how this impacts kind of the liquid side of what we've been talking about. So this is that treatment train again. If you slide, we went through the treatment process. And I'm going to stop right here. This could be basically every plant here has some form of this. Some plants just end here and they go to a truck. And this might be belt presses. You can swap that out, whatever. It's a dewatering piece of equipment. How many of you have like some sort of blend tank ahead of dewatering? See, one hand. Mountain Creek, you have a small one. You have a small digester. What do you guys have? You have a blend tank. How big is it? How is it? Well, okay, so it's pretty big. So this blend tank, does anybody have a blend tank that's more than 2 hours that it sits in there? I see one hand. Well, yeah, Cruz does. Looks like Wilson Creek has one that's bigger than 2 hours. What's going on in this blend tank when I add primary sludge and WAS? going on in here? It's mixed. It's well mixed. What are they going to start doing? It's anaerobic, right? What do we talk about in there? And what's that first form of digestion that we talked about? Hydrolysis, fermentation. Fermentation's happening in there. And Leon's going to get into a little bit of dynamics of what's happening in here tomorrow. If we have an anaerobic tank with PAOs, our phosphorus bugs.
Releasing phosphorus.
Yeah, so when Paul was talking this morning on the phosphorus side, PAOs uptake and release phosphorus. They uptake phosphorus in the aerobic zone. They release phosphorus in an anaerobic zone. So if you have a blend tank, you're doing bio-P, this configuration can cause you very big headaches if you have a P release in here, because that P release then goes to watering and your phosphorus load comes back to your plant. That's where we talk about this liquid solids interaction. Yes, this part here is more complicated. There's a lot of things going on here, but even this part here, most people have a blend tank. And it's a big thing of how big your blend tank is. If you keep it small, then you can reduce that risk of P release. If you keep it aerated, you can reduce that risk of P release here. But essentially, P release is one thing. The fermentation is what I want to focus on here. In this tank, so what you're looking at here is VFA production. The VFA production is the orange line going up, and then we have WAS production in the green line. And essentially, the x-axis is a blend tank HRT. So as the blend tank is sitting in there, the TRI blend tank here has about a day HRT. They can actually hold sludge for a day. And we're just using 20 hours as our example. So that sludge, that WAS and primary sludge is sitting in there for 20 hours. We go up, our VFA concentration in there is 2,500 milligrams per liter. They have around an MGD of recycle. So if we go up here, once I go to this dewatering here, this is about 1 MGD going back to the head of the plant at 2,500 milligrams per liter. Oops. So we're going to start in your next few pages. We should have, we're going to have worksheets. So we're going to start doing some whiteboard things. We'll see how well it works, and maybe next year we don't do any whiteboard things. But I left some blank pages so you can kind of follow along. But as an example, if we're talking about this 2,500 milligrams per liter coming back at 1 MGD, we're talking about 20,850 pounds per day. VFA is coming around. So we're going to skip forward to this. What we're going to be looking at now is this kind of interaction here. I'm going to draw that whole plan here on the board. And we'll start kind of marking some of this up. Let's do, yeah. Is that not visible? Watch. Try to, if you want to write down on your scratch paper, you can. But essentially, if we're operating that blend tank at 20,000 at 20 hours, we've calculated that we have 20,000 pounds per day of VFAs coming back around. Right? So this is happening every day. What's happening to that 20,000 pounds of VFA? Staying in the system. Does VFA get broken down?
It's consumed in ABs.
I heard it gets consumed in the ABs. Why the ABs?
Or not consumed, it's DFA.
One of the primary clarifiers.
Yeah, it's typically not moving process, so yeah, it's consumed.
There we go. Particulate and soluble. We're falling over I think what his analogy was, we have the floaters, the sinkers, the lurkers. There we go. The lurkers. VFAs are the lurkers. Is our primary clarifier removing lurkers? No, we've got to rely on it coming to here. So this VFA is coming into here. That's 20,000 pounds more coming in. If we do Paul talked about yield. Remember that VFA coming in and he showed a bacteria. Remember some of that carbon went into here, some of that carbon goes to CO2. So if we let's assume 50%. Just throw a number out there. Let's say 50% of that is now yield. So now that 20,000 pounds is now coming out in our waste. So our WAS has now increased by, let's just say, let's use 10,000 pounds per day. That's how much the WAS has increased. Is everybody following along here on that load? And this is where we started to get into these liquids and solids interactions, and basically what the impact of those are, and where in the plant those impacts happen. So this increased WAS starts coming back to our blend tank. What if we don't waste it? What if I keep my wasting rate as it is now? Causes a buildup in the secondaries. What do you mean a buildup?
Wasting the extra 10,000, gonna back up, cost larger blanket in the secondaries.
Larger blanket, our mixed liquor is going to go up, right? We're essentially taking that WAS. If we don't increase our WAS, and we have 10,000 more pounds per day, that mixed liquor is going to start to creep up on us. And so essentially the scenario, what we're going to set up here is there were basically capacity processing issues in the solid stream. So now we can't increase our waste because we had issues. I can't remember if it was belt press issues and getting to the belt presses. They had some belt presses offline. They couldn't get belt. This was before the digesters were there yet. They had one digester online, so they're in this limbo of construction where you're kind of got half your plant here and half your plant not. They had capacity issues here, and so they started storing here. At the same time this was happening, so you had 10,000 more pounds coming back because your blend tank's running full all day. They couldn't empty the blend tank because of capacity issues. We have gravity thickeners. What are gravity thickeners kind of good for? I mean, they gravity thicken, right? But what can you do with them?
If they slow them down,
I can slow them down. Why would I want to slow down?
you can reduce the primary flow.
Yeah. If I have capacity issues, well, geez, I'm that gravity thickener is now a tank to me. What's going to start happening in that tank? Septic. We hear that term again. Septic. What is septic? Septic, it's fermentating. What starts happening here?
Overflow, bad overflow.
The overflow of the gravity thickeners. What's in the overflow?
COD.
Yes, COD in its form of BFA. Anybody, I don't, Mike, Rodell might know, or Russ or Daniel, what was the concentration when you have an upset thickener? What's the BFA concentration or TSS even concentration coming over?
Then we had 2 to 3% solids.
I say minus 30,000, 20,000 is not uncommon.
So he's talking about 20,000 milligrams per liter coming over the weirs because of capacity issues. So that's 20,000. Let's say you have 20,000 coming back here. That's TSS.
Yes.
Where does that get removed at? Where's this 20,000 pounds of TSS getting removed? Getting removed in our primaries, right? But it's coming right back. It's coming right back. And that solids, as you keep cycling it around, it's gonna keep breaking down. And you're gonna start making more VFAs. Let's use 2,000 milligrams per liter VFAs coming out. I'm just gonna put a number unless somebody corrects me if that doesn't sound right. 2,000 milligrams per liter coming over the weirs. What primary sludge flow? What is your overflow? Anybody have an idea of approximate?
Over two records.
Over the weirs of gravities.
Oh,
Close.
3,200 GPM. There's a
It's got three small ones on mine.
That's a question for you.
Yeah, he looking for GPM.
I got 4.6 MGD. 4.6 MGD coming off the primaries.
Primary?
Or off the thickeners over the weir. So 4.6 times, we're using 2,000 milligrams per liter. That's 8.34. That's 76,000 pounds. I think 4.6. Are you guys sure on the 3,200 GPM? That sounds high.
Yeah, that sounds pretty.
That's what we feed into the gravities.
Yeah.
So we're 10,000.
Let's go half of that. That's too high. This is all for, let's say it's 35,000 pounds here. Again, coming back in here. Where is this BFA getting removed? Is it getting removed primary clarifiers? No, coming here. We're gonna use half of that again. Plus, so half of that is 17,000 pounds per day. But we can't waste more because we're having capacity issues here. So what's happening in our ABs again? Blankets are building up, mixed liquors are going up. Cruise liquid, and I heard somebody up here say, when this BFA was coming around, you know what solids guy's talking when he says that's liquid's problem now. So essentially now we have this basically 27,000 more pounds per day we're producing. We're producing that much per day.
That's how they used to do this.
And you remember, this is a large plant, so this is actually, it sounds huge if you're talking about like a 5-inch plant.
Yeah, I got both kinds of it, so.
But, okay, so normally they're operating at 5,000 milligrams per liter. Let's use that. Let's use 55. How high did you guys get liquids guys at Cruise? How high did that mixed liquor go?
7,000 something.
I thought I heard an 8 at one point, but we'll use 7. We'll use 7,000 as the number. So that's 1,500 more milligrams per liter per basin. So the liquids guys are bailing out the solids guys by storing solids.
Yeah.
Essentially, these aeration basins, they're still processing. They still met permit. Your mixed liquor is getting up. Management of peak flows becomes very difficult. Your blankets are getting how high? Too high. Blankets are getting very high in the clarifiers. So if we were to use 1,500 milligrams per liter extra in there, how big is an aeration basin? 3.6 million gallons times 12 of them. How many pounds? I mean, let's take. Who wants to take a swag at how many pounds you think liquid stored for solids? Throw a number. I had a number already.
7,000? A lot. At least
540,000 pounds is what the aeration basins were storing.
Days worth of processing.
It's
Except you can't process it. So essentially, when we talk about how liquids can kind of impact each other, now at some point you get to the point where, hey, we have to, now we're going to bring a full circle here. We have to waste. Liquids finally, I think Steve got on the phone and said this can't happen anymore. We've got to process. So what solids folks, when you heard we need more WAS, what did you do?
Turn the primary down.
Turn the primary down further,
That's
bring more WAS in. But they got the WAS, they started bringing the WAS down. What do you think that does to a digester that's going through startup right now?
messes up your ratio.
It messes up the ratio. I used to have 50-50 coming in. Now I'm going to load it up with WAS. I think at some point, primary sludge may have been turned off sometime. It might have been 100% WAS for a
I
while.
don't think it was
Try to
down.
catch up.
We were definitely down.
It was down.
300.
So when we talk about like being like in terms of how things can cycle on you, this isn't anything an operator did. Operators are basically trying to manage the capacity they have during commissioning. And this is kind of just to show you how things can kind of just amplify on you and start really to cycle out of control. It didn't get out of control, I shouldn't say that. They managed it. It was some times where we're looking at numbers and we're like, wow, those are some high numbers.
Yeah.
What did it do to the digesters? Remember, we're not talking about TSS anymore on the solid side. We're changing that composition, and when we go down here, we start looking at our proteins, our carbohydrates, our fats, and we start looking at what the composition of all of those are. WAS is heavy on the side of the proteins. It's going to have more amino acids and have more nitrogen. What happens to that nitrogen when it goes into a digester? Makes ammonia. What's the concentration of ammonia in the digester? We're at 2,300 milligrams per liter. What were you doing this event?
Yeah, close.
There were numbers that were 3,300, 3,400 milligrams per liter in a digester. It's around, sorry, I'm here, right, it could be really bad. Around 3,400 milligrams per liter in the digester. And we talked about big changes to bacteria and how well they react to it. Ammonia is the gas that can kill us. It's also a gas that bacteria don't like either. when you start talking about 3,400 milligrams per liter, a portion of that 3,400 milligrams per liter is ammonia, and a portion is ammonium. So you start increasing that, you start to see impacts to the digestion process. They started to see acid build up in the digestion process. And essentially here's kind of the way it went during that over last fall. The green line, let's do the blue line is basically the primary sludge. Going up and down. Our green line is our ammonium in the digester. So our primary sludge hovering on the 60%. Primary sludge actually went up to 70%. Probably when liquids really helping them out by storing things. They're storing things, but then liquids gave a phone call and said, we can't do this anymore. They went from 70% primary sludge ratio down to 50%. So not a huge, not a crazy swing. But look at and they stayed down there. Look at how quickly that ammonium started catching up with them. And then they basically came out of it, and that ammonium started coming back down. But it's essentially, you've really got to start making sure you're having these open communication conversations with both sides of operations. If you're having a capacity issue on one side, maybe there's something you can do to help solve that. Maybe there's not necessarily something you can do. But really what happened when this flag went up of, hey, we can't store this anymore, that's when I think basically you brought in outside resources to help belt press more sludge. They brought in more belt presses. You had to move sludge out of the plant. And that's something that needed to start moving, because if you start getting wet weather events, the liquid side wasn't able to take much more flow. And so it's kind of full cycling into this ammonium. We tried to keep this afternoon focused on nitrogen. Now we're back to this ammonium. So in a digester, we're actually releasing ammonium in there. And that's all coming back as a liquid to our mainstream processes. Yeah.
So
You can try to do the math on how many pounds of ammonium that is. It's about 11,500 pounds of ammonium. So I'll get to, so here's the, kind of jumped ahead, but how does nitrogen end up in our biosolids? Paul went over, how do we grow nitrogen, or how do we grow bacteria? Remember that C to N to P ratio? Some of our biomass is made up of the C to N to P, and if that ratio is off, if you have too much C and you're nutrient deficient, you can really have a poor performance in your system. But either way, basically your bacteria have some components of nitrogen in them. And so when we have this WAS, that's where it's coming from. When we actually look at our plant, what TRA is set up, essentially is it's like dashboard where they can look at process performance and data. But essentially when we look at our primary sludge, we've got a 4 to 6% nitrogen by mass on primary sludge. When we start looking at WAS, we're talking about 8 to 10%. It's about double. So when we switch that WAS, when that WAS primary sludge ratio flips, now that's why you saw that spike in ammonium release. You're breaking down solids. Your digest is doing what it's supposed to. It's breaking down solids, and it's increasing that load. When we talk about what the load coming back is, typically when we look at the load coming back in ammonium, it's 15% of the influent nitrogen. 15 to 20% of the influent total nitrogen. So I'd say 11,000 pounds. I think Cruise has somewhere around 40 to 50,000 pounds coming in per day. So this is a significant load. This isn't insignificant in terms of the recycle load coming around. And then really you don't have too much release they have pre-dewatering. You don't really have a lot of release of nitrogen in your storage tank. So everybody here who has a blend tank, you're not going to see high levels of ammonium. The biggest thing on your blend tank that you're going to see is phosphorus. And that's what Leon's covering tomorrow. He's doing basically what I did here. Leon is covering in depth and kind of advancing what Paul started on the basics of phosphorus, going into phosphorus cycling, and also going into kind of the latest in phosphorus removal with RAS fermentation. So he'll be covering a lot of that. We have about 45 minutes left.